Example 4. So this is one of those more extensive questions where we're going to study the nature of this function f of x, looking at its domain, asymptotes, interval of decrease, increase, extreme values. So I know extreme values I'll be relating to f prime, concavity, points of inflection. So I know this part relates to f double prime, and then sketch the graph. So let's tackle this one by one. Domain of f, well, we know that any ln function, this part x to the power 4 over x minus 1 must be greater than 0, must be positive. And notice how the denominator x minus 1 means that, well, there must be a vertical asymptote at x equals to 1. And if any number that is less than 1 but greater than 0 is sub into the denominator, I will get a negative value, right? Which implies that the domain of this function is x that are greater than but not equal to 1. Part B. On what interval does f increases or decreases? This is related to the gradient of the tangent. So now let's first find the derivative of f of x. F prime of x, we have ln of a function is 1 over the function. So 1 over the function is x minus 1 over x to the power of 4. And then we have to take the derivative of x to the 4 over x minus 1. We can use quotient rule. I have 4x cubed times x minus 1 minus x to the power of 4 times the derivative of x minus 1, which is 1. And then divide this whole thing by x minus 1 squared. Okay, let's see what I can simplify here. The top part here, inside the brackets, square brackets, I have 4x cubed times x, which is 4x to the 4 minus x to the 4, 3x to the 4 minus 4x cubed. Outside the brackets, I have x minus 1 in the numerator and x minus 1 squared in the denominator, which means that this is going to be x minus 1. And then x to the power of 4 goes here. I can reduce some of those powers of x, and I will get 3x minus 4 over x times x minus 1. We're interested in extreme values as well, and also when the gradient of tangent changes, they occur at f prime equals 0, potentially. So let's set f prime of x equals to 0, which implies that 3x minus 4 over x times x minus 1 must equal to 0, which means that x is 4 over 3. Okay. If I evaluate my function at x equals to 4 over 3, it will possibly give me an extreme value after I test for intervals of increase and decrease. Okay, we'll generalize everything in the chart at the end. But for now, for part C, I will just evaluate the coordinates of this function at 4 over 3. Okay, what do we have here? We have ln of 4/3 to the power of 4 over 4/3 minus 1, this gigantic thing. The denominator is 1/3, so we're multiplying by 3. This is ln of 4 to the power of 4. And then 3 to the power of 4. Wait, hold on. No. Okay, so this is, what's 4 to the power of 4? 64 times 4. 6, 2, 5, 6, 27. Okay. D. Determine the concavity of the graph and find a point of inflection. I will take my result here. This is my f prime of x, and derive that again. I'll differentiate that again. F double prime x is derivative of the top 3 times x minus 1 minus, well, this is x squared minus x in the denominator. So the derivative of that is 2x minus 1 times 3x minus 4 all over, that's gross. That will do. If I expand and simplify, and after some magic happens, you're going to get negative 3x squared minus 3x plus 8x, 5x, plus 3x is plus 8x. And let's see, plus 4 minus 4. X squared, x minus 1 squared. Can this be factored? Well, if I factor out the negative sign from the top, I have 3x squared minus 8x plus 4. I think so. I think this can be factored into 3x. X here. Positive 4. I can get 2 and 2. Then 6 and 2. Yeah, if I minus, negative 6, negative 2 is negative 8. Good, works. Okay. X squared, x minus 1 squared. We're looking at concavity, so let's set this equal to 0 and find the possible locations of the points of inflection. So looking at the numerator that we have, x is equal to 2 over 3, or x is equal to 2. Now notice how x equals to 2 over 3 is not in the domain, because x must be greater than 1, right? So this cannot be counted. This is the only possibility. Well, let's look for the position. So f of 2 is ln of 16. Because 2 to the power of 4 is 16. 2 minus 1 is 1. Yeah. Very good. Now, let's use a chart to test out these intervals of concavity, increasing, decreasing. All right, so looking back, we have a key point at x equals to 4 over 3. Nothing goes beyond 1. And then we also have a key point at x equals to 2. Let's pick a couple of test points. So I'm going to use x equals to 1.2, x equals to 1.8, and x equals to 3. Okay, I already know that this is 0, this is 0. And plugging in 1.2, f prime at 1.2 is negative. F double prime at 1.2 is positive using calculator. F prime at 1.8 is positive. F double prime is positive here. f prime of x is positive when x is equal to 3, and double prime is negative. Okay, so what does that mean? I notice that we have an interval of decrease between 1 to 4/3 because of the negative sign of f prime. To the right of that region, I have an interval of increase for x greater than 4/3, which implies that there is a turning point at x equals to 4/3, and it is a local minimum, or it can be the absolute minimum in this function actually. So absolute or global minimum at 4/3 ln, what do we say, 256 and 27, I believe. And then for concavity, it's up, up, down. So concave up, anywhere between 1 to 2. Concave down, anywhere x is greater than 2. And then we do have a change in concavity. So point of inflection happens at 2 and ln 16. Let's make a sketch. Okay, so put in the VA. This is x equals to 1, x-axis, y-axis. It 4/3, so 1.1/3, somewhere here. This is a local min. And then 1, 2 is about here, somewhere here. We have the POI. So decreasing, increasing, change. And here is a sketch of f of x.